power of being able to use energy and potential energy, kinetic energy, comes with this idea of conservation of energy, which comes from our work, kinetic energy theorem, which says that our total work, or our net work, is equal to the change in kinetic energy. Well, we now know when we have conservative forces, right, this is equal to our minus change in potential energy. So writing this out without the deltas there, that means that this is kinetic energy final minus kinetic energy initial is equal to minus the same thing. And I can do some rewriting. I'm going to multiply this minus sign through like this, and I'm going to collect my initial and final terms. So I'm going to add Ki to both sides. Right, so those go away to get all my initials, and then I'm going to add UF to both sides so I can get the final. And what I get is kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. What this says is that our energy, kinetic plus potential, we call our energy, sometimes our mechanical energy, our energy initial is equal to our energy final, assuming we don't have any friction right here. And we generalize this to say our energy is conserved, and we define now mechanical energy as kinetic plus potential, and then we often have thermal energy that comes from our friction. So when we have frictional interactions, what happens to our mechanical energy, like when something slows down, that kinetic energy goes into heating the surfaces in friction. And so that goes into thermal energy. So we can say our energy is still conserved when we broaden what we mean by energy, not just mechanical energy of kinetic plus potential. But what this says is that very often it's easier to look at some problems in terms of energy conservation, or sometimes it's our only choice, rather than doing F equals ma. The first immediate thing you can see is, hey, there are no vectors here. So my preference is to say, can I use energy conservation to solve a question before I look at forces, just so I can avoid vectors? And so one way that I find it useful to think about this is to think about drawing bar charts for the energy. So I'm going to just do it with an example. So if I have a situation where I start with a stretched spring where I've stretched it and I'm about to release it. So I just release it. So I start it from rest and it's stretched some distance x. Okay, there's my spring. So that's position 1. Position 2, this is my, x equals 0, my equilibrium. Position 2 will be when I'm somewhere right about here. We'll call this x middle for right now. That's fine. And then position 3 will be when we're at the equilibrium position. The spring is at its relaxed state. So when it's at rest, we let it go. It heads in this direction. So right here, this has got some speed, right? It's going in that direction. And here, it's going even faster, right? For position 3. So I can create bar charts basically that show how the energy is interacting. So if I look at this at position 1, okay, so this is position 1, I can write what is my spring potential energy and what is my kinetic energy for position 1. Well, in position 1, all of my energy is spring potential energy and I don't have any kinetic energy. So my kinetic energy is not there. And in position 3, we're going to skip to the easy one, right? I have kinetic and potential. 3. At that point, there is no spring potential energy because our x is equal to 0. And so if I use my equation, which I was looking for, but I don't have, spring potential energy equation. U spring equals 1/2 kx squared. So in this case, all of my energy is in kinetic energy, and there's none in spring energy. So if this is some amount, say 3 joules, what I have over here is that this is going to be 3 joules. And so in this intermediate space, in 2, sort of my x distance is maybe half the size, which means my potential energy is about 1/4 what I had. So maybe it's this much is my u. I mean, it depends on the value. And then the rest of it is my k, such that these two add up to give me 3 joules. So I just need to know the energy at one place, and I can tell what's going on anywhere else in my system. And so I like these energy diagrams because it shows how the energy shifts from potential to kinetic. You don't have to have one being 0. You can be in this intermediate stage where you're sort of halfway in between. You've got some speed, but you still have some potential energy left. And notice at 3, it's not coming to rest. I don't have any friction yet. So it's going to go and it's going to oscillate, and then it's just going to keep bouncing back and forth if this is happening on an air table. Even though I've set this up for only the situation where we have no friction, we can still use this setup, use these bar charts to talk about friction, because what we can do is redraw. So if we say the same situation with friction, we can redraw these charts to say 1 is going to be the same, right? Our U, and we have our kinetic energy. This would be 1, but then by the time we get to 2, what happens is we've reduced our potential energy to be some amount, but we don't get quite as much kinetic energy. Like this is our K, and then we have a little bit of energy that's gone into thermal energy. So this is thermal, and altogether these 3 now add up to whatever we had. So if we had 3 joules, this is still equal to 3 joules. We can figure out this thermal energy by saying this quantity as a positive quantity would just be the absolute value of our friction force times whatever distance we went. Okay, in this case, it would be the difference between x and x sub n. Okay, so we can still add it up. So that would be in position 2. And in position 3, assuming the friction didn't bring it to a stop at that point, we would have potential energy of 0. We would have a kinetic energy that's like this, some amount. And how big it is now is going to depend on the numbers, and the thermal energy is just going to continue to grow. Okay, so that's thermal and kinetic. And so if we wanted to write this as an equation, we could say E initial is equal to E final plus whatever work we had to do associated with friction, or thermal energy right there. These two need to add up. If it actually stops, then of course our mechanical energy, so maybe we even want to write this as mechanical energy to separate that out, but what we could say is that our initial kinetic and potential energy is all going at the end to just this friction energy. Okay, so we can still use it even when we have non-conservative forces. It's just what happens is that this just continues to grow. It never gets less. We don't get it back in general, unless you get it back sometimes if instead of doing it in terms of thermal, for example, on your electric car hybrid, you can have regenerative braking where what would normally have been a thermal loss of taking your brake pads against the wheel turns into electrical energy to recharge your battery in a hybrid or battery operating system. And so then you actually can get it converted back to mechanical energy. There are some losses in that conversion, but you can get some of that back.